Okay.
Yeah,
Thanks.
like Francis said, Uniswap contracts are divided into two parts, the core and the periphery. The core contracts, they handle pair creation, protocol implementation, functionalities like swap, mint, burn LP tokens, etc. And the periphery contracts are the contracts to call to interact with the protocol. It's actually recommended to, if you want to make a swap or add liquidity or etc., it's recommended to make a call to periphery contracts that redirect your call to the core contracts rather than directly interact with the core contracts. And my contract that I'm going to talk about, the factory contract, is very simple contract. It handles the creation of a new liquidity pool, the pairs. It creates only smart contracts per unique token, and it contains the logic to turn on the protocol charge. I'll move on to VS Code. You can see my VS Code?
Yeah.
Okay, cool. So just look briefly at the interface of the V2 factory. It contains mostly view functions, and the most important function in the contract is create pair, which creates a new pair of. Basically, you have two addresses of token A, token B, and it creates a new contract and it returns the address of that pair of the contract of that pair. And there is other two functions that are not view functions are set v2 and set v2 setter. Basically, they set the v2 and the v2 setter that I'm going to talk about in a second. So if I go to the contract, as I said, the main contract functionality is this creation of new pairs and handling the setting of the v2 and v2 setter. So what are v2 and v2 setters? Now Uniswap V2 charges 0.3% charge for each trade, and this 0.3% goes to liquidity providers. But in the future, it has the possibility to actually take a 0.05% cut, and this cut will go to the address V2. For now, the V2 address is set to the address 0. In the future, it can be set to something like a multi-sig wallet for Uniswap Treasury. And the address V2 setter is the address that is allowed to change the address V2 or also change the V2 setter, basically change itself. And then afterwards, we have mapping from address to address to address. Basically, mapping get pair, basically get pair address of token A, address of token B, it returns the address of the liquidity pool of this pair. And this mapping is symmetric, meaning that get pair token A, the token B is the same as get pair token B, token A. And if there is no contract of this pair, it returns, obviously it returns the address 0. Then we have an array of all pairs that contains the addresses of all the pair contracts. And an event emitted when after the creation of a pair, it emits an event with the address of the first token, second token, the address of the new contract of the pair, and the uint that it emits. It's basically when you create a new pair, you append the address of the contract to the all pairs array, and then when you append it, it increases its length. So the uint emitted here is basically the all pairs length. And the token 0 here is always less than token 1 because addresses are hexadecimal and you can rank them. So always we always have the token 0 less than token 1. In the constructors, basically what it does is just sets the v2 setter address, and that's all. Then the all pairs length simple function returns the length of the all pairs array. And I'll just skip this for now. I'll just start by these two simple functions. The set v2 basically sets the v2 address, and obviously only v2 setter can set it. The same for set v2 setter. The v2 setter sets a new v2 setter address, and only v2 setter can call it. So the main function of this contract is the creation of a new pair contract. So in argument, you have addresses of the two tokens, token A and token B, and it returns the address of the new pair contract created. So first it checks that the two addresses are non-identical. Then here it sets token 0 to be the smallest between token A and token B, and token 1 to be the biggest. Afterwards, it checks that token 0 is different than address 0, and only one check is sufficient since token 0 is the smallest one. And then it also checks that this pair. Yeah.
Sorry, I just have a question about the token A less than token B.
Yeah.
How do you measure how do you compare the addresses?
Addresses are hexadecimal, so you can convert them to numbers.
Hi guys.
Okay.
So like an address is the representation, like 16 plus 16 times something, then plus 16 squares times something, you know, like binary representation, but for 16, not for 2.
What's the purpose, do you think, of comparing one address to the other? I didn't really understand why they were doing that check.
The comparing one address, because you cannot create a pool with the same token. It doesn't make sense to have a pool with the same token.
Sure, but it could be bigger, couldn't it? It just has to not be equal to it, doesn't it?
Sorry?
Could it just not be bigger? So as long as they're not equal, presumably then they're not the same token. But the address could be bigger than it, couldn't it?
They check first that they are not equal, but then they don't use token A, token B. They use the new token 0, token 1, and they use them so that token 0 is actually the smallest one. If you see here, they compare.
I see.
Token A.
Yeah, I see. Okay.
Token A is less than token B, then token 0 will be token A and token 1 will be token B. Otherwise, it's the inverse.
Mm.
I think it's just useful that when you emit an event, you always know that the smallest token is this one, and also here you only have to do one check, or maybe for gas savings, I'm not sure. But like it's nice to have things in order. So maybe it's that. Anyways, moving on. Then yeah. Also they check that the pair have been created yet. So you check that the mapping token 0, token 1 is equal to others 0. And then afterwards, this is the interesting part. This is the here we create a new pair contract. And then we get its address. I'll just, because it's the most complicated part, just come back to it in a bit. So suppose now we created a new pair contract and we have its address, its pair. Afterwards, we call the pair contract, and we call the initialize function in the UniswapV2 pair contract to initialize that pair. I think Philip later is going to talk about the pair contract. Afterwards, we update the mapping get pair token 0, token 1, and get pair token 1, token 0. But we set both to be equal to address of the pair contract, and then we push the pair contract to the all pairs array and emit the event. So coming back to this part, the creation of the pair contract in Solidity, you can create a contract in 2 ways. Either using the create opcode or create to opcode. If you use the create opcode, you create the contract, but you cannot know in advance the address of the contract that you are going to deploy. But if you use the create to function, actually you can know the address of the contract that you're going to deploy before deploying it. For example, here, if we just wanted to create a new contract with the create opcode in a normal way, we can do something like this. We assign pair contract to be a new UniswapV2 pair of token 0, token 1, and then we get the address pair to be equal to address of the pair contract. So to understand how that works, I actually have a little demo on Remix. So here I have a simple test contract. It has just two variables, owner and num. It has a constructor that sets the owner and num. It has a simple function to set the num. And what I want to do is actually create a test contract, but to create it and know its address before deploying it. So how that works, first you have to get the bytecode of the contract to be deployed. Then you can compute the address of the contract to be deployed, and I'll show you how that can be computed. And afterwards, we're going to deploy the contract using the create to opcode, and see that the address that we get after deploying it is the same that we computed before deploying it. So I'll call the contract that is going to deploy this contract. I'll call it factory2, and I have an event that will emit the address of the contract that is deployed in the third step on the salt. So first I have an internal function to get the bytecode of the contract to be deployed. And how do you get the bytecode of the contract to be deployed? So first you have, this is the contract that I'm going to be deployed, the test contract. You wrap the test contract in type, and then you call the creation code property. So you get a bytecode. But you also, to get the bytecode of the contract to be deployed, you have to append this bytecode to data that is going to be consumed by the constructor. And in our case, in the constructor of this contract, we have to feed it the address owner and uint num, which is I'm going to append to that bytecode, and I'm going to return it by this function. If we come back to the Uniswap contract, they actually do the same, but since if I go, yeah, in the UniswapV2 pair constructor, the constructor doesn't take any parameters, so they don't need to append when they compute that the bytecode using type UniswapV2 pair dot creation code. They don't need to append any data, but if your constructor need to consume any data, you need to append it before to the bytecode that you obtain here.
Just a quick question on where you say of type, so type parentheses test and type parentheses Uniswap V2 pair, is that something that's a Solidity native thing? It's just something that
Your XR, eh?
Yeah,
sorry.
Yeah, well, the creation code is the type and contract dot creation code. You get the bytecode of the contract that is going to be deployed. It's related to how Solidity works in a low level. Like I don't think I can. I mean I just know how to compute the bytecode, but I cannot explain it in a low level. So for now,
No, that's cool. I thought that was pretty interesting.
okay, cool. So I'll just move on. Here I have the function that compute the address before deploying it, and I'll just come back to it later. So now first you have a function that get us the bytecode of the contract to be deployed. Then here we're going to deploy that contract. So in the parameters we take, I take just the parameters of the parameters that I'm going to feed to the constructor of the contract to be deployed. And uint salt, it's an arbitrary value provided by the sender, which is me. In the case of Uniswap, you can see here that the salt is equal to the ketchup of the ABI encoded token 0 of token 1. Even the salt in the case of Uniswap is deterministic. If you know token 0 and token B, you know the salt that they are going to feed to the create to function. So afterwards, I get the bytecode of the contract to be deployed that using the get bytecode function that I defined. Then I just declare an address, and And to use the create2 function, you need to use it with assembly. So I just wrap up the code in assembly here, and the create2 function takes 4 parameters: v, the amount of it to send. In assembly, for example, if you want to send some money to the contract before when creating it, you can use the call value. In the case of Uniswap, they just use 0, so that's also known in advance. And then the second parameter is a pointer to the start of the code in memory. So you have to give this add bytecode 32, the bytecode we created, and add the add 32 to it, because actually the actual code starts after skipping the first 32 bytes of bytecode, because the first 32 bytes are reserved to store the size of the code, and the size of the code is the third parameter you're going to need. Uniswap, they do the same here in this line. And finally, you have to feed it a salt, which is like I said, an arbitrary value provided by the sender. But Uniswap, they give an arbitrary value that is deterministic. You can associate, you can know it in advance. And then this is just something to check that the contract was created. And then afterwards, I emit an event with the address of the here I set the address to create2 create the return value of the create2 function. So and the address will be the address of the contract deployed, and I emit an event with this address and salt. And afterwards, I'll compare the address I get with this function that computes the address before deploying the contract. So how to compute the address of the contract to be deployed? Actually, the addition of the create2 opcode was part of the AIP 1014 by Vitalik, and in the specification here you can see how the address is computed. You do the Ketchak 256 of 0xff. First I have to get the bytecode of the contract to be deployed, so I store it in bytecode. Then I have I declare a byte32 hash, which is the Ketchak 256 of 0xff, which is this to get all this in one variable. You have to ABI encoded like that, and then first thing you need is 0xff. It's this one. Then the address of the creator of the contract, which is address of this, and then salt, which is a salt that we're going to provide. And finally, the kickback of the init code, which is the kickback of the bytecode we computed before. But the address is actually the last 20 bytes of this. This will return at 32 bytes, and we want only the last 20 bytes. So we get them like that, like from 12 to 32. And then so now when I compute that hash, I get actually the whole 32 bytes, and I have to call the last 22 bytes of hash to get the address. So how you get that? You cast the hash into a uint256, and then you cast it again into a uint160 and get the address of that. This is just how I copied this from a YouTube video. So I'm just going to do a little test to show you how that works. I will deploy the contract, the factory contract. I'll grab the address of the contract that deployed it to feed it to the functions here. First, I'm going to try and get the address of the contract I'm going to deploy before deploying it. So I give it the address. These parameters are the parameters of the test contract owner and num. We'll set num to be 10, and we'll take a salt maybe 15. I'll call it. So it returns an address. And now I'm going to deploy the contract, and hopefully the address of the contract deployed will be the same as this one here. So again, I'm going to call the deploy create to. Here I had the two functions. I had even deploy create to show you that if you use the normal way to deploy, you're not going to get the same address computed. So we'll use the deploy create to. We'll give it the same parameters, num 10, salt 15. Yeah. Yeah, this is the transaction of the creation of the new contract. And if I scroll down, yeah, here in the logs, because when I deploy create, I image an event with the address of the contract deployed on the start. You can see that the start here is 15, and the address imaged, yeah, it's the same as one as the one that I computed before. So yeah, I think that's it for this part. So basically, they create a new pair contract with a deterministic address, and yeah, that's it. So if you have any questions.
That was pretty cool.
Yeah, thanks so much for the demo.
Well, thank you very much for the demo. I may have a question, but it might, I don't know if it is so relevant, but I'm a little bit new in this. So I gone through the Uniswap code in GitHub, and I did not see something like a migration files. Like no, you normally use when you use TOEFL to do migration. Why is it?
I don't know, they didn't use truffle to I don't know, I think the repo is the repo of the contract. They have a test folder where they test the contracts. I don't know what framework they use, or maybe someone can give a better answer actually.
Yeah, if I can jump on that. So just to add a comment, not necessarily an answer. So yeah, like you said, you can develop Solidity with different frameworks. So Truffle is just what's our main focus at Consensys. That's what we're taught with. But there's also Scaffold, EAT, and there are other ones as well. So just seeing a migration is more consistent if you use Truffle. That's when you would see that. But if you're not using Truffle, it could be that might not be there, or most likely wouldn't be there.
Okay. No bid now, right?
Yes, sir.
All right. Yeah. I'm a little bit late, but I enjoyed the demo. And how often is this?
Once a week, every Wednesday.
Oh, that's nice. Okay.
It's always posted on the group.
Is that?
It's always on the group. There's always a notification on the group.
Okay.
We have a meetup group, so you can join that, and then you will be notified for any new events.
Yes, I joined the meetup this afternoon. Then that's when I saw the event.
Okay.
Yeah.
Yeah, you will, and also you can join the WhatsApp chat group as well.
Oh, that's nice.
It's also on the Meetup website, the Meetup group website.
Okay. Okay. That's
Sorry to ask though. So
Yeah.
are you also you're an ex-Consensys student, right?
No, I'm still a student in Fortis.
In what? I didn't get that.
I think he lost connection.
Bara, I have a question actually. It's Artyom. Can you just a little bit explain why we need to use salt? Maybe some very specific questions.
Okay, I'll post the link of the AIP 1014. If you just read through the specification, this is actually how the address is created. You need to feed a salt to the create2 function. It's just part of the specification, actually.
So this is some like random number, like we just add like, yeah.
It's up to you. It can be random or it can be deterministic. It depends. What do you want to do? I mean, in the case of Uniswap, if
yeah, I understand it's like can be calculated in
Uniswap,
advance.
like, they have the salt is the ketchup of the encoded pack, the token 0, token 1. So
yeah, we can
know the salt before everyone knows it. So the address of the contract that is going to be created is known in advance, and you can also compute it off chain. So
okay, yeah, thanks.
So as far as I know, I think if you want to say create your own address that you like, there is a website that allows you to create your own address that you like. You can actually use SOAP to try to get that address. You just try various SOAP, and then you can get the address that you want.
Sorry guys, my a laptop, I forgot that I didn't put it on light, so it went off. I'm sorry. I was answering a question then before, but you can finish what you're doing. They're saying sorry about that.
Okay, shall we move on to V2 pair?
Can I just ask a very simple question before we move on? That's okay.
Yeah.
I'm sure this is a bit of a silly question and probably out of context, but why do we need to know in a deterministic manner what the address is before we deploy it? I'm missing like the 10,000 feet view here.
yeah, well, actually, that's a pretty good question. I didn't understand the reason why, but first, if you compute the address in a deterministic manner, you can look it up off-chain. So there is, and also you can send money to that contract before it is actually created. If if it is useful or it makes sense for your use case to send the money to the contract before it's actually deployed. And yeah, that's the two main reasons I found. If anyone
I think another reason I've seen is so you can, if you have a protocol and you have a system of smart contracts, you can make all the addresses look similar. So like you can have them all be like 0x801 like whatever you want the company address to look like, instead of being a whole bunch of random addresses.
Yeah, so you can, if you look at the Uniswap V2 addresses, they are the same across all the chains, different test network, and that's how it is created using the create2 function.
Do we think that's required from a sort of practical reason, or is it just because they like doing it? Or I'm just understanding the logic for doing that, because that was sort of fairly involved, wasn't it? And I was just wondering, am I missing? Well, obviously you need to do that because of X, Y, Z. Yeah, maybe I'll have a look at the contract in more detail, but yeah, just wasn't fully sure why they needed to do that.
So if you're talking about practical reason, usually if you have let's say you need to create an account for a client, you can create an address for the client to send money to that account, and if the client didn't end up sending or using the account, you don't spend any gas on creating the account, because that is done off chain. But if let's say the client ends up using the account and send money to it, then you can create it and start deploying the contract on that account.
Okay, that makes sense. Yeah, I get it. Cool, that makes sense.
Yeah.
Thank you.
Okay, let's move on to V2 pair then.
Yeah, let's start with V2. Let me share the screen. Do you see?
Yeah.
Cool. Okay, so so this is the pair. So basically, where the whole logic is happening for swapping, burning, maintenance of the balances for each token. So yeah, here we have at the beginning we have all of the imports. From what is interesting here is the math, which is like allowing us to avoid overflow with all of the mathematical equations. So if we add or multiply, so we will not overflow over bytes. The next one, which is also super interesting, and we found that last week, is this library, which is allowing us to have decimals. So what they basically did, because in Solidity you don't have decimals, you have just integers. Basically, they took 256 and divided for 112, 112, each like first one for before decimal and the second one after decimal. So that's how they got basically all of the fractions. Yeah, and the rest is just imports from their own contracts. And here's actually the factory that we just were talking. And as we talk, the factory is happening in the construct of this contract. Okay, so yeah, then if we go a little bit below, here's the safe math and for decimals. So here's the minimum liquidity. So they need that to avoid also dividing by 0. Here they are creating from bytecode also some selector for transactions. Here's the address for factory, for token. Here's the reserves for each token. So how much is in the pool? The timestamp of last block. All of the parameters. I mean, this is the cumulative sum of prices basically. This part is pretty interesting. So this is all of the locks that are happening. So the re-entrancy would not happen. So basically, they are locking the function to execute and then unlocking it after execution. We can see it, for example, if we jump to the swap, it's happening before the swap. So first is locking it to 0, and then it's executing all of the function. It's happening because of external costs to some other contracts, as we can see in here. So we need to lock that function so that will execute, and also we'll see that check all of the requirements happening, and after this whole function happens, then we unlock it back. So if we now jump to and we can jump for this swap as a first function. So this is like a typical requirements. They are checking if the amount is bigger than 0, getting the reserves, checking if the amount is smaller than the reserve. If any of that is wrong, then it will just stop executing. Here they are creating local variables for balances. Here is actually the same. Here's just checking if the 2, so the 2 is address. So the 2 address is not the address for token 0, and it's also not for token 1. So it will not swap to itself. Some more checks, and then safe transfer. If the amount 0 is more than 0, then transfer. Here is also transfer. to be honest, I'm not 100% sure what is happening in this part. I didn't go so deep. Maybe later on someone will be able to cover this part. Yeah, then it's calculating the balances for each of the tokens, and then is basically calculating amount in for each one of the tokens. If one and another check here, basically, and basically adjusting the balances, which ones once again are checked, and then if everything is fine, then it's updating. It's firing the update function, which will go in a second, and at the end is just emitting swap event. So if we go now to update, so in update, so we are just update. So swap just is happening, and here we will update the balances of the reserves for that particular pool. So yeah, once again we are checking here for. I assume this is for if there is not if there is not overflow. So if everything is fine with bytes, calculating the last time. I mean time from the block. This is interesting part actually. So they just make it because in here they have only 33 bytes because of how they structure all of that. So to get basically longer time in this block time, they just modulo for a bigger number, just to get longer distance between block times. And I think that this is like over 100 years, if I'm wrong, correct me. Yeah, and basically here, okay, so here they are calculating if this is the first block or not. If it's the first, then it's the first exchange. They basically created that variables and adding it. And then if it's not, then basically they update the reserves and the time of last block and emit sync event, and that will basically finish for us the swap function. So that was the swap. What else we have here? Initialize. This is basically initializing tokens. I think here we have get reserves, so just reading the global variables. So and then okay, so we have all of the minting. Basically, the mint is collect on the liquidity pool providers when they add to liquidity pools, so they can mint additional tokens as a reward. So yeah, once again we have all of the logic. I don't know if we really want to go in deep into all of that. Basically, logic for minting reward for whoever is in the add to liquidity.
One thing I was interested in was the UQ112. I think you just glossed over it in the update function, like how they actually do the maths on decimals.
You mean here?
Yeah.
Okay.
Okay. Yeah, I think I get what they're doing there.
Yeah, it's okay. I didn't go very deep, but I see it's they're encoding this, basically getting the reserve 1 and dividing it by reserve 2. I mean, reserve 0 and then multiplying it by the time. So it's like a average price per that period of time. So I don't know, from yesterday up to the moment that is happening the update. This is like a time difference basically. Okay, so yeah, the minting, yeah, same. So update is also happening when someone mints from the pool, and I assume the same is happening. No, actually not. So yeah, the burn is basically when they are withdrawing, I assume, from the pool. Yeah, what else we have here? Sync. This is just for synchronizing, I assume. Yeah, they're just calling update here. This is, I assume, also not the most important. Say transfer. Yeah, so that's basically it. I think that the most important part from all of that was learning about how to make a decimals, I mean fractions in Solidity, and safe math was pretty interesting to learn, and as well the modifiers and the reentrancy problem in this language. So yeah, that will be basically it. Any questions? I don't hear any questions.
Thank you, Philip.
Yeah, thank you.
Okay, if there is no question, maybe we can move to the next contract, which is so we are done with the Uniswap core. Hey, sorry, we still have one more, the V2 ERC20.
Yeah, I put my hand up for that. I can go on that. It's an import for the V2 pair, so works out. Give me a sec to share my screen. Oh, the Zoom only allows you to share the whole window. Wait.
Are you not able to share this document?
I'm trying to share it, but I think because this is my first time using this laptop for Zoom, so saying I have to quit and reopen. So I might quickly do that, just ducking in and out. Bit awkward, but yeah, give me a minute to get back in the call.
Okay.
Sure. Or maybe, would you guys want to start with V2 router?
Doesn't sound like it's going to be very long, but.
Okay, we'll wait a bit then. We can take a break. We can maybe take a 5 minutes break.
Okay.
Yeah.
Okay, let me try to share that again. Okay, this looks a lot better. Yeah, can you guys pretty much see this?
Yeah.
Okay, cool. Yeah, it's giving me all these question marks. I was trying to share my screen. It's like, what is that? Anyway, so first presentation, so I didn't know how in depth we wanted to go and how much time we're going to spend on each contract. So I thought I might just focus on what I thought were the interesting parts. And I guess basically what it is, pretty much for Uniswap issued ERC20 tokens, they don't actually use the Open Zeppelin implementation. So I guess we're used to, hey, importing at Open Zeppelin ERC20, but they seem to have their own implementation. Most of it's the same as the ERC20 code, and I'm going to assume that we're familiar with that, so I'm not going to waste time on that. But yeah, primary use case is the Uniswap LP pair, which we just went over. It's an import on that, so pretty good to go right after that one. And so, yeah, we just saw this, so don't worry about that. And this is pretty much the interface. So this is all standard ERC20 stuff. Where it gets interesting is what I've bolded here. So the domain separator, permit, type hash, nonces, permit. So pretty much it all centers around this function here, the permit. And I think Francis has gone over this a little bit in his article that is written up. But essentially the point of the permit function is so that, so with, it's the annoying thing with ERC20 tokens is you have to approve them and then transfer them. If another smart contract is calling the transfer from function on your ERC20 token, and that's 2 transactions, and that gets really annoying, especially when gas is really high. So the permit function essentially lets us do that transaction in one shot. And basically you sign a permit, and then that's sort of your gasless way of doing the prove step. And then that will once if you have the right signature with the permit, then that lets you do the transfer from one step. And then the domain separator, permit, type hash, nonces, they're all parameters inputs to the signature, which is the EIP712 signature. It's a pretty, let me just go down to interesting parts. Yep. So it's a pretty, probably I should have, best thing I should have done was to prepare a demo like Brad did. I can do that next time if there's time. But it's actually pretty, I found it pretty hard to create the signature, like EIP712 signature myself. Whenever I've tried to do it from scratch without helpful functions, it's always taken me like at least more than an hour to do it, to create an EIP712 compliant signature. So it's actually, yeah, if you don't have the helper functions and the code ready, it's very like specific on how to create it. But yeah, going into the actual, so this is the interesting part of the code. And so essentially domain separator, permit type hash, and nonces, I guess the basic high level point of all of those is to create a signature which is unique to that instance of calling the function. So domain separator here, if you sort of look at the elements, so cat256, and what you're trying to put into that signature is well, you've got the pretty much the important part here. Pretty much the main point of the domain separator is to make sure that the signature is unique for that particular contract that you're calling it from, so that you don't have a collision between different signatures between different smart contracts. And so, say like you said, so parts, I guess interesting parts are, so you've got the name, cat 256 bytes name, and the chain ID and the address this. And so you can you're sort of trying to make sure that this is the unique signature for this chain ID. So for example, the Uniswap V2 router you have the same contract address on different chains. So making sure that you're creating a signature for just unique for that chain, address this, make sure it's unique for this particular contract address, and bytes name, make sure it's unique for this particular name which you choose for this domain. So that's the point of pretty much the domain separate, is just to make sure that this is a unique signature for this particular domain. And in this context, the domain is this smart contract. The permit type hash, so coming up here, it has the address owner, the spender, value, nonce, and deadline. You're pretty much trying to make, so domain separator makes sure that you're creating signature for that particular domain. So here you're trying to make, and then for that particular domain, you want to make sure that it's a unique message that's being created. So the owner of the token, of the ERC20 token, who's trying to spend it, how much you're trying to send is the value. Nonce is how many times you've called this permit function in the UniswapV2 ERC20.sol contract. So if you use the permit function, if you've never used the permit function before, nonce will be 0. And then once you use the once, it's 1, and then 2, and then so on. And deadline is, in the UniswapV2 context, it's pretty much the block timestamp, which is a deadline for this transaction to happen. And then if your transaction goes through after the deadline, then it fails because by a requirement statement. I'm sort of going outside of, I'm sort of referring to code that's not on the screen, and my apologies. I should have done that so it flows better. But yeah, so that's sort of the permit type hash, is to make sure that this signature has that this signature is specific to the intentions of the person creating the signature. Make sure that you're sending the amount that you want you're sending that, you're permitting this contract, so the spender, to send this amount, the value, to and the person who owns the token is the owner, and nonce to, and you're putting the other parameters to make sure that this is the right function call. So that's the permit type hash. And going over what the nonces is. And sort of just going more into the constructor. So basically you see uint chain ID, assembly, chain ID, just basically using assembly code to get the chain ID. And then you're using, you're creating the domain separator in the constructor. And so next part, so the actual permit function. So yeah, if you look at the first line of the permit function, the required deadline has to be more than or equal to block timestamp. Yeah, so it'll pretty much revert the call if the current timestamp when the transaction goes through is past the deadline. And then the actual digest, so then the next line, bytes digest equals ... That's the hash that goes, that's pretty much your signature, your permit signature. And if you sort of dig more into it, so cat 256 and then ABI encode packed, this is all per EIP 712 specifications. which I put a link to later on. The X19, X01, that's part of the specifications, and then domain separator, we've gone over that. And the next part, cat256 ... that's pretty much the permit type hash. So essentially your signature is you ABI encode the X19, X01 plus the domain separator plus your termit type hash, and then you hash that in cat256, and then that gives you your EIP712 signature. And then next part, address recovered address equals eco cover digest. So pretty much the eco covers, it's a native function in Solidity, which you pretty much put in your signature and then the VRS components of a signature, and it confirms, sort of gives you an address of who's created that message. So VRS pretty much, it's pretty much the signature of the message, but then it's split down into the VR and S components. That's something I can get into another time, and apologies again, this is a lot clearer with code that's going through step by step. And then required recovery address. So the next line requires making sure that you're not recovering the zero address, and you're making sure that you're confirming that the creator of the signature is the person that's actually, that you're pretty much confirming that the signature has been created by the owner. And then approve is the ERC20 function, and that's pretty much goes back to what we were saying before about it's a way to do the approve function called ERC20.approve without in a single transaction. And so if I go to the next step, yep. So this is pretty much what I was trying to say, but if you go to the ERC, so this is that's linked to the ERC UniswapV2 documentation, and then so pretty much they explain that all the UniswapV2 pool tokens support meta transaction approvals via the permit function. This obviates the need for blocking approved transaction before programmatic interactions with pool tokens can occur. It's pretty much saying that instead of for the smart contract to like transfer ERC20s that you hold to somewhere else, you have to do the two-step approve and then transfer from. But this sort of scheme of doing things lets you do it in one transaction. And it's going to ERC712. Yeah, so instead of using the approve ERC20.approve to prove that, you're approving the smart contract to move your tokens, you're using the permit scheme and using an ERC712 compliant permit scheme signature to do that. And then next, so yeah, we use ERC712 compliant signatures to prove that the person who called the permit function owns the UniswapV2 ERC20 salt token. And then this is, we went a bit over this, domain separator, the permit type hash, and the nonces. You're pretty much trying to safeguard against signature collision. So making sure that your signature is unique to that particular domain, to that particular LP token, ERC20 token, and that you're trying to protect against forged signatures, and that the signature is exactly what the owner intended, this value and this deadline. So we can go a bit into the docs. I've gone through this a few times and I found it like pretty confusing myself. And maybe I believe this is something for your own interest because it goes pretty in depth, but I guess the key thing is that there's a helper function for ethers.js. So they have the signer.sign type data function. That's probably the easiest way to create an EIP712 compliant signature. And if you sort of go into it, it's, yeah, so you pretty much need to, so you have 3 parameters here, domain, types, and value, and they're pretty nice to give you an example here as well. That, okay, domain is pretty much, you specify it like that, and it's really tricky because you have to get every single part of it right, and then your types looks like this, and then your value goes in that. And I guess the reasoning behind why it's all, it'll probably take I feel like it'd be a 1 to 2 hour thing to go into how the EIP712 thing is structured. Could be an interesting topic for another time because I've seen EIP712 signatures around quite a lot. But yeah, this is probably the most headache-free way to create an EIP712 compliant signature. But yeah, for me personally, I've just found the headache either way. And then going back to the slides, the other thing to note is that the eco cover function, there's been some debate over that you should use ECDSA.recover instead. Some of the reasons are that the eco cover recover signature can give you a 0 address. And we saw in the UniswapV2 code back here that they actually have a guard against that, like recovered address that can't equal the address 0. And you can also, there's a high chance of forging signatures with ecover as opposed to ECDSA.recover. So that's probably a topic for another time. But yeah, that's pretty much my summary of the Uniswap ERC20 code. So most of it is pretty much the ERC20 implementation that I'm assuming that we're familiar with. But yeah, the interesting part is all around the permit, and I feel like it's quite a few layers deep to sort of get the step-by-step of how and why things are structured. But basically, yeah, main thing that is trying to let us do is to let us sort of, instead of doing a 2 transaction process of approved and transfer from, just lets us do it in 1 transaction. Does anyone have any questions?
Yeah,
just a comment, really. Oh, go ahead.
I was just asking, how if you can give an example how the permit function works. Is it for providing liquidity or?
So if let me quickly try to, so UniswapV2, I think it's remove liquidity with permit. They have this function. And then, I think it's better to go into GitHub, UniswapV2 router. This is where I've seen it used. So this is where it's used in the Uniswap context. So this goes into another contract, but they have this function here on the router, Uniswap remove liquidity with permit. And when you deposit liquidity onto Uniswap, and then you have your LP tokens, and then you want to remove your liquidity from Uniswap. This function is called, the remove liquidity with permit function is called, so that you can remove liquidity in a single step. And I'll try to go through and I'll try to see if I can find any particular, probably easy if I can find an example, but if I can find the UniswapV2 router,
So the
Hopefully this
permit
is it.
permit is basically
not-
just for removing liquidity, just to spend the Uniswap LP tokens.
In the Uniswap context, yeah.
Because you can't provide liquidity without permit, because in that case you will be providing other ERC20 tokens that does not have the permit.
I think with approving liquidity, you have to approve it first. Maybe they haven't add liquidity with permit function here.
You can, because
Okay, yeah, they only have remove liquidity with permit.
yeah, because only the LP tokens have the permit.
Oh yeah, you're right, yeah.
Okay.
Yeah, so if we sort of go into it here, UniswapV2 pair.permit, yeah, so pretty much that's where the permit functions used in the UniswapV2 system. So if we sort of quickly go through the function here, and this is sort of outside the scope of ERC20, you're getting the address of the pair using the UniswapV2 library.pair4 function, and then you int value equals approved max. That's pretty much saying it's going to be infinity. So it's pretty much going to be like, what's the value that you're going to approve to move? It's either going to be the going to be the maximum possible UINT value.
Yeah, you can choose. I mean, you can,
okay.
If approve max is false, then is true. Then if approve max is true, then you give permit for the max amount. Otherwise, if it's for the liquidity amount that you want to permit, yeah.
And then, yeah, that's the permit function there. That's pretty much giving permission for the Uniswap V2 router to move your Uniswap LP tokens. And then this is a remove liquidity call here. So yeah, I think to sum it up, the sort of utility of the permit is to, so if they didn't have the permit, then you would have to approve the Uniswap V2 router to move the LP tokens out of your wallet and burn them. But with the permit, then it's a single step transaction to remove liquidity. Because the removal liquidity is basically the LP tokens move from your wallet and they're burnt. Someone can correct me if I'm wrong. And then in exchange, the LP token gives you back the ERC, the liquidity. So for WEF, ETH/USDC, it'll be giving you back ETH and USDC.
I have another question actually. The permit function, does it work only for the Uniswap contracts, or you can permit any other address?
You can permit any other address. So I've seen it used, I think the other utility I've seen it for is deposit with permit. So you can, like you can sort of deposit tokens in a single step. Instead of saying like, hey, this contract has to approve I have to approve this contract to move my tokens and then let it transfer from, and then just let it to be a single step. So I guess the sky's the limit as to where we can actually, I shouldn't say that. I guess that's another utility I've seen of the ERC20 permit function. I think OpenZeppelin actually have a they actually have a draft ERC20 permit function here, and then they have their own implementation of how they do the permit. So yeah, interesting is the Uniswap V2, they have their own implementation, so they don't seem to use OpenZeppelin imports. But yeah, you see here that they use the ecdsa.recover instead of the ecocover in the Uniswap V2 contract. But yeah, I think the main like high level overview is that you're trying to remove the approve step, approve transfer from to transaction process.
Yeah, I mean, I've seen them being used lately also like a whitelisting process. If you combine it with NFTs, right? You have a few options. You can whitelist tokens to a specific person, and the 712 signature comes out as a good layer in between, instead of storing some claim codes on chain or storing a Merkle tree. You can basically share a permit-based signature with the person who wants to claim, and then he claims basically a token with the 712 signature. I'll look up for an example. It's pretty generic. I know I was playing with it, but yeah. That a comment in terms of 712.
Yeah, I think ERP712 is pretty versatile. It's whenever you want to. I mean, we can try to gloss over if we have time. Francis, you can stop me if there's no time. We try to gloss over this and see if there's anything that we can pick out. Basically, you're trying to sign a meaningful message. And so like basically in a Uniswap V2 context, you're trying to sign a message that, hey, I want to let the Uniswap system to move my Uniswap LP tokens out of my wallet. That's probably the simplest way I could put down why ERP712 is used in the Uniswap system. But pretty much any sort of message that you want to sign and make cryptographically secure is what you can use ERP712 for. I don't know if they go so much into applications here. They go more into the reasoning behind it. So maybe this isn't such a great place to look for applications. You probably leave this for people's own interest. Yeah, I found this myself a headache to go through this stuff.
Great.
Yeah, the signature is a very complex area. I think we can probably do a full session just on that.
I actually used some of this technology for my Consensys Bootcamp final project. So it's interesting, I didn't actually know about this standard, but I ran into a lot of the problems that this is obviously solving. So I created like an NFT project where rather than minting up front, I had to sort of mint on the fly, because what I needed to do was I basically had this project where you connect your wallet, and then the Etherscan API checks the date that you did your first Ethereum transaction, and it mints an NFT based on the date that you first did your first transaction. So clearly you can't sort of you can't do that up front. You need to do it on the fly as the user connects. Now, initially I sort of built this and I thought, well, I'll just create the sort of NFT contract in a fairly standard way as per ERC721. But the mint function for that sort of took the year that they first did their first transaction. So then I was thinking, well, actually, someone could easily just go onto Etherscan and just interact with the contract directly rather than going through my web app, because the web app had all the logic in for checking when they first connected via the Etherscan API. So I kind of solved that problem by using signatures. So that I use the EC recover function that you just highlighted to basically check that the transaction, the contract call, had actually gone through my dApp. So it's pretty versatile from what I can see. And that's just my experience with using this once, but it feels to me like you're sort of able to force people to go through dApps, which is quite nice, rather than interacting directly with your contract. So I need to scan and sort of putting whatever parameters they want into functions. So if you force them to go through a dApp, clearly like your dApp can call the function with a specific set of parameters that you control. So it feels quite powerful actually. But yeah, I wish I'd known about this 712 standard and some of those ethers.js functions you mentioned, because I had to pick it all together myself. And I'm sure the way I did it is full of security vulnerabilities that this standard probably seeks to resolve. So yeah, super interesting. Thank you.
That's really interesting. How you put it, like forcing people to go through your dApp. That's yeah, that's a PowerPoint.
Yeah, it's interesting because I was Googling that. I was like, how do I force someone to go through my dApp? And actually, like, I intend to write an article on this because there's very little out there on how to force people to go through your dApps. Most answers, just to like on Stack Overflow, just say you can't. They're saying, you know, the contracts on the blockchain, anyone can interact with it. And yes, they can. But if one of the parameters to call that function obviously is a signature, and you basically have to have been receipt of the private key or some sort of private key to produce the signature that allows you to call that specific contract on the blockchain, then you can force people to go through your dApp. So yeah, it's quite interesting, I think.
It could be, yeah, it's probably a good topic for another, like I feel like we probably need to block out an hour or two to sort of go through ERP712, if that's a topic of interest.
Yeah, I'd be interested in having a look at that for sure.
We can actually do that. Like, let's say, for example, before the pre-post post on Wednesday, you can just say maybe 1 hour on Saturday or during weekend or something like that, if that works.
Yeah, we can fix a session for that. Looking through the various applications of the EIP 712. As far as I know, there are a few real world applications like DAI token is actually also using the EIP 712 permit. From what I read, the Pancake Swap token is also using that. Okay, thanks for sharing, Jefferson.
No worries.
Now let's move on to V2 router, which is also very interesting. Do we have Thierry Kev? Because he signed up for the V2 router. Is Thierry Kev here? Looks like it's not. Or anyone else want to share? I haven't looked through in detail myself.
Let's look at live.
Sorry?
Let's look at now. I mean.
Oh, okay. I can go through the V2Migrator first because I'm responsible for that, and then we will come back to V2 router later. If we have time, it's already, what time is it now? It's almost 8:30. Okay, let me go through the V2Migrator. So the V2Migrator is actually quite short, but there are a few interesting details that I think will be very useful. So basically, what I explained at the start, V2Migrator is for user to migrate their liquidity pool from V1 Uniswap V1 to Uniswap V2. So in the constructor, in the constructor function, you have the address of the factory V1 and the address of router. This router is actually the V2 router. And it's just initializing the factory address and the V2 router. And then we come to the and this receive This is just for the contract to receive ETH,
Hey,
and
Francis,
then
sorry.
Hmm?
Can you zoom in? Can you zoom out a bit? I mean, like
Oh.
zoom so we can see.
zoom out. How do I zoom out?
I think command plus plus. Yes, yeah, you're using a Mac, right? Or
I am,
Windows?
yes.
So just hold
Command.
command and then click plus plus. And plus plus plus.
Plus plus.
Doesn't work. Yeah. Just hold down command and click plus.
All
plus
right.
there.
Okay. 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 Is that good?
Yeah, I think it's much better.
Okay. Right. So next function is the migrate function, and this is basically the interesting one. You put in the token address, and the reason why you don't have two tokens is because in Uniswap v1, the liquidity pools only consist of ETH and another token. So there isn't like two tokens with. So all the liquidity pools have ETH and another token. So it's so the other token will be ETH. And then you have the amount token minimum, the minimum token amount and the minimum ETH amount. And address 2 is basically the new Uniswap liquidity pool in the V2 pool. And the deadline. Deadline is the expiry date for this function. So first of all, you the function gets the V1 exchange.
What does it? Why does it override? Does it inherit from another? Because the migrate is an override function. So does the contract inherit from another contract?
Inherits the interface, the V2Migrator interface. What's your question?
I just wanted to know why it's override if it inherits from another contract. So.
Oh, why is there override? Oh, I see. Yeah, because it inherits the interface. And when you inherit for another contract which has the same function, then you have to use override. So in this case, the interface basically will have the functions that you are using here, but there is no implementation details. So the implementation details are in this contract. Yeah.
Is it always like that in Solidity? Is it always like when you have interface and interface have the same method as implementation, you have to use override? Or, because that for me looks a little bit strange.
I didn't know that you like usually you override when you inherit from another contract, not an interface.
Yeah, like implementation.
I think you probably need to open up that so we'll know if it's actually an interface or a contract. That's where it inherits from. Because most likely, I'm also thinking it's a contract as opposed to an interface.
It's both interface and contract. If you look at because I work on the AirSwap contracts, and it is following the same pattern. So basically, you have an interface, and then the contract will inherits the interface and will override the functions in the interface. So yeah, it applies to both interface and contracts.
So do you have to declare the interface function as virtual as well?
Interface function. Let me
I think in the interface, it just has to be an external function.
Yeah, it's just external. Can you see?
Yeah.
Yeah.
Okay, that's interesting.
And also this is I can't remember, this is from certain version of Solidity and above, because the older version does not have this override requirement. Yeah, okay. So moving on, so this is to get the liquidity pool address. So get exchange token from the factory, from the V1 factory. And then this is getting the amount of the liquidity. So V1 balance off message of sender, and then require so this is to make sure that the transfer from function actually returns true. If it's not, then it will show transfer failed.
So when you wrap the function inside the require statement, you execute the function and then check its value, right?
Correct.
Okay,
That's correct. Yeah, moving on to this remove liquidity function. So remove liquidity function have a few arguments. So the first one is the amount, which is liquidity V1, and then you have the minimum ETH withdrawn, and then you have the minimum tokens withdrawn, and you have the deadline, the time after which the transaction cannot be executed. So this is setting the deadline to the max, I think. Yeah. And then this is using transfer helper. So I would like to show you what transfer helper is. Transfer helper is basically, it contains all the safe approve, safe transfer, safe transfer from functions. And the reason why Uniswap uses that is because some tokens don't return true or false after the transfer, or after this they execute these functions like transfer from, approve. Some tokens don't return true or false, so you don't really know whether the transaction has gone through or not. So with this safe approve, safe transfer, and so on, it ensures that the token, when you execute the functions, it will return a true or false. So we can look into a bit more detail here. For example, the safe approve function. So this is actually a low-level call. It will call this encode with selector is a function selector, and this is basically so every function has some certain digits. So this is basically calling that, and what it translates into is this one. So it's translate into approve function. And the reason why is because it's bypassing the Solidity checking mechanism to because we are implementing it, we are not using the tokens transfer from function or approve function in this case. And it requires this function will return a true, will return two outputs. One is this true or false, and the other output is data. And basically we need to check that it returns true if successful. And this data can be optional, it can be 0. But if it returns something, then it has to be true. So we need to make sure both of these requirements are met, and then the transfer is successful.
Yeah, I think I saw already this kind of calling where basically data length of data is 0. That means something failed on the way.
No, that in this case, data length equals 0 is not fail. It's just saying that there isn't any data return. But it's saying that there could be two possibilities. One is that there is no data return, is 0, or if there is a data return, then it has to be true. And both of these has to be true for the transaction to be successful, to be considered successful. And this pattern is implemented across all the other functions you see. It's all the same kind of pattern.
So let me just understand. So if there is no data, basically the length of data is 0. Yeah, no data returned. What does it mean then? Is it all fine? I mean, we call that function, everything goes well, or we basically something goes wrong?
From what I understand, if there is no data, it just means that you only transfer the amount, because when you execute this call function, if it's successful, you don't really need to know whether there is data or not, right? Because when you do this call function, it can return that the amount has been transferred, and or there is a value that has value in the form of data that has been returned. I haven't looked into what kind of data that is being returned.
Cool. Okay.
Yeah. I can look into that later. What kind of data is being returned?
Anyway, it's pretty interesting that you can call functions by passing I think hexagonal or whatever is the 0x095. This is like some kind of address, or maybe not address, but some kind of signature of that method. Yeah, that's pretty interesting to see. And you are saying that then we are basically avoiding some kind of checks.
Yeah, this is basically avoiding using the functions within the token itself, because the token would have implemented its own functions like for approve or transfer, but we are avoiding that, and we go into the lower level. This is a low level call, so we are going into a lower level and implementing the function ourselves.
I think it could be interesting if we do a session on the low level calls in Solidity.
Yeah. I'm writing down all the ideas.
Yeah, I think I really like the permit idea, going through the permits. I saw also some use cases somewhere, but it would be definitely good to understand better.
Okay, cool. So I will now go back to the migrator function, migrator contract. So this is to approve the token to be used by the router, and this is the amount of the token, the liquidity pool. And the next line is using the router function to add liquidity. And if the amount of token 1, if amount of token V1, this is the V1, the V1 liquidity pool amount is greater than the token V2, then we will have to approve the token to be transferred to, oh, sorry, then the amount that is used by router will be 0. This is to change the reset allowance to 0. And then the next line is basically transfer the amount of token from to the sender, and that amount will be equal to token V1 minus token V2. Otherwise, it will be the reverse, basically.
I think I lost something.
Yeah, I didn't.
So why the token? Token V1, token V2. Okay, sorry. Yeah, now I have it. Okay. Yeah. Token V1 is basically the whatever is the different token, and then token V2 is for version 2, basically.
It's for the liquidity pool.
Yeah.
The V2 liquidity pool. Yeah.
So it's not token, different token, is the same token, it's just version 2.
It's the same token, but it's just the V2 liquidity pool.
Yep.
Yeah.
But a quick unrelated question. What extension is the arrows? That looks pretty useful.
What, this?
Yeah, that.
I'm not sure.